Hello, I would like to welcome you to lecture 26 of 2FH3. We'll start now the third part of this, actually not the third part, the fourth part of this course. In the first part we talked about vector analysis, second part we talked about electrostatics, third part we talked about magnetostatics, and now in the fourth part we'll talk about time varying fields. What will happen when the currents and the voltages start to change with time. And as we'll see, there will be a coupling between the electric and magnetic fields. We cover chapter 9 from the book of Sadiku, pages 399 to 410. So far, all the examples that we have covered were all statics, and things were not changing with time. The charges were static. The flowing currents were steady, so they were not changing with time. But in many applications, like in antennas, if you have an antenna, what you will do, you connect an antenna to a time varying source, and this time varying source will start to transmit bits, as shown here, maybe sequences of ones and minus ones or ones and zeros. It may be transmitting an AM signal, so it will transmit a sinusoidal signal whose amplitude will be changing with time, or whose frequency will be changing with time, or can transform any other type of waveform. For all these applications, we have to consider the variation of the fields, and as you will be seeing soon, there is actually a coupling between the electric and magnetic field in this case. This area of time varying fields started by the work of people like Faraday and Ampere. And years before Faraday did his famous experiment, it was known that electric current creates fields. So we have already known that if you have a current flowing in a certain conductor, then there is a magnetic field created around that conductor, and it simply it encircles this current. When Faraday had his observation, it wasn't really intentional. He was in the lab. He had a loop of current connected to a voltmeter, like as shown here, and then he had a nearby loop of current connected to a voltage source. And then when he closed the switch in this circuit, which is completely disconnected from this other circuit, he noticed a deflection in the avometer. The avometer will give a deflection. He noticed also when he opened the circuit, the avometer will also give a deflection the opposite direction. So the deflection actually would not happen if the switch remained closed for a while. So this deflection in the avometer will only happen at the moment when he opens or closes the switch. This led him to believe that the current, when he closed the switch, he changed the current flowing in the circuit from 0 up to a certain value, and this change in the current created a change in the magnetic field, and this magnetic field coupled to the other circuit, and this coupling created a voltage or a current in the other circuit. This was the first time they were able to show that variation in the magnetic field can give rise to electric current or can give rise to voltage. So this is called Faraday's experiment. It's a very famous experiment, and it opened the door for many interesting things in electromagnetics. Faraday's experiment led to the formulation of Faraday's law, one of Maxwell's equations. It's very famous. They call it Faraday's law, or call it one of Maxwell's equations. It's simply saying that when you have a flux changing with time, here we talk about the flux linkage. So if there are a number of turns, then we get the flux linkage is equal to the flux multiplied by the number of these turns. If the flux linkage changes with time, then there will be a voltage difference created that is trying to oppose that change in the flux. So mathematically, the EMF is equal to minus d lambda by dt. And of course, as we agreed, lambda is equal to n psi. Psi is the flux, where psi is obtained by carrying out an integral over the surface of the loop or the surface of the circuit of B dot ds. For example, let's take a look at this diagram that we have here. If you have the flux, the magnetic flux density vector B in the z direction as shown here, and it's increasing with time. Then the flux going through this one loop is also increasing with time. Then d psi by dt is positive because it's increasing with time, and this gives rise to a negative voltage difference. You can see here we have this polarity, plus and minus, but so this polarity here, because of this point is higher in voltage than this point, it will result in a current flowing in this direction. What is this current trying to do? This current is actually trying to create flux opposing the change in the original flux. If you have a current flowing this way, then it creates a flux in the shown direction. So you can see this created flux is trying to stop the increase in the original flux. And this is actually a phenomenon that happens very often in nature. Nature is trying to resist changes. So if you have the flux be increasing with time, this will result in this voltage difference shown here across the resistor, that result in a current flowing in this direction that will give rise to its own magnetic field trying to resist the change happening in the original magnetic field. Now, even if you take this resistor out from the circuit, you will be able to measure a voltage difference between these 2 points. This is what's called by E dot dl. So E dot dl is simply to carry out an integral around this contour, and then you'll be able to see its value, positive or negative. Now, one word of warning: if I select the normal to the loop in this direction, then dl has to be taken according to the right hand rule. Okay, this is why this voltage here, even though it is shown as plus minus, it is negative with the direction of dl. So now we know something very interesting. When you have flux going through a circuit changing with time, it will create in your loop or on your number of loops some voltage difference. And if you close the circuit, this will result in a current flowing. What is this current trying to do? This current is trying to oppose the change that happened in the flux. Mathematically speaking, we can write this expression here, that the integral of E dot dl around this closed loop, which gives us the voltage difference that we are observing here, is not zero anymore. It's not zero. It's equal to minus the rate of change of the flux. And this, of course, happens when we have a single turn. If you have more than one turn, then you have to include n here. So now we moved from the conservative electric field that we have earlier, where the integral of E dot dl over a closed contour is equal to 0, to the integral of E dot dl is equal to minus partial t of the flux is equal to negative rate of change of the flux. And the negative sign is simply saying that the voltage created will be such that if the circuit closes, as it's happening here, it will try to create flux that resists the increase or decrease that's happening in the flux. So this is really the statement of Faraday's law in integral form. Of course, I can convert this line integral, closed line integral, into a surface integral. So we can convert this one to an integral over the surface of curl E dot ds. And when you equate this side with this side, you see that every point in space, curl E must be equal to minus partial b partial t. So before, in the statics case, we knew that curl E is equal to 0. Now we know that in the time varying case, the electric field lines can be closed lines because they are created by the rate of change of the magnetic field. They are not only created by charges anymore. Curl E is equal to minus partial b partial t. Faraday's law has many interesting applications. The first one is the basic concept of electrical generators. Here we have a coil. Okay, it's connected to a brush. Forget about the brush part for now. You have a loop, and this loop will start to rotate it around its axis. So its axis here will start to make it turn this way. Okay, so it can rotate around this axis. Now the flux going through it, that it's put inside a magnet, so there are flux lines moving from the north to the south in this way. Okay, this flux will these magnetic field lines will create a flux through this area. But because we are forcing it to rotate, we are actually changing that flux with time. The definition of the flux is equal to the integral over the surface of b dot ds. Then we have to take the dot product between the normal to that surface and the vector b. I'm here showing you a side view. This is the normal here, this is ds, and this is b. d dot ds will result in the cosine of this angle, cosine of theta. In the shown diagram here, the angle theta is 0 because they are in the same direction. But if you rotate the plane of the coil a little bit, there will be an angle between them. And if you make it horizontal, the angle between them is 90 degrees. So if we, in a typical dynamo, water or by hand movement, you make this coil start to rotate around this axis, then you are changing the flux going through it. The flux is by definition the integral of b dot ds. So it's equal to b ds cosine theta. Theta here, the angle theta between them is changing with time because we are causing a movement. And if we assume that we are causing it to rotate with an angular frequency of omega, we can replace theta by omega t. So when time t equal to 0, theta will be 0. When omega is equal to when t is equal to 2 pi over omega, theta will be 2 pi, and so on. So by doing that, you will see that I can take the cosine out, and the integral of b ds will give you the maximum flux. The maximum flux which we have when the coil is in the shown position here, the vertical position. So now this is a flux going through the circuit, and you can see it does change with time because we are causing this loop to keep on rotating with an angular frequency of omega. Now, according to Faraday's law, the electromotive force that can be measured between these two terminals, between the terminals of the coil, is minus d psi by dt. And if you differentiate this one relative to t, you get minus sine multiplied by omega. Minus will cancel with minus, then you get omega psi naught omega sine omega t. So in this between these two terminals, you can measure a sinusoidal voltage. So, and this is really the basic theory of electric generators. You have a number of coils turning inside a magnet, very strong magnet. So they keep on cutting the flux lines. The flux going through them is changing with time. As the flux is changing with time, this will give rise to EMF. And this EMF will be such that if you close the circuit, it will create a current that will try to resist the change in the magnetic flux. So if the magnetic flux is decreasing, it will try to create a current that will increase the magnetic flux. So this is one possible application for Faraday's law, the concept of an electric generator. Another interesting example is the concept of a moving loop. So here you have a loop where one edge is moving at a constant velocity. There is a flux B going into the page. It's a uniform flux, not changing with time. So here the tricky part is that there is no change in time for the flux. The B itself is constant, but the psi going through the circuit is increasing. Why? Because if you carry the integral of B dot ds, because the area is increasing with time as this edge is moving, then psi becomes a function of time. Psi is actually increasing. So in this case, there will be some change. This will create an EMF in the circuit, and then you can calculate the flux. You can calculate the current. Now, there are two ways of calculating this current. The first one is, as I explained to you earlier, calculate psi as a function of t, so it's the integral over the area which is changing with time of b dot ds, and then try to find this as a function of t. And this is not really a problem because this length is changing with time. So the area will be a constant length multiplied by a variable with time, so this will give you psi as a function of time. And then differentiate this one relative to time, and this will give you what is the EMF, and then you divide by the resistance. This will give you the created current. One other way is to go back to the motor equation that we had long time ago. We said if you have a conductor moving in a magnetic field, then there will be a force, actually not a conductor, if you have a charge moving in a magnetic field with a velocity u, then the force affecting that charge is QU cross B. So in this case, we can divide by Q, and then we say force over Q over charge will give you magnetic electric field. But this is not a typical electric field, it's an equivalent electric field. So this electric field is trying to push the positive charges in its direction, and the negative charge is opposite to it. So in this figure, for example, this is the direction of U, B is going into the page, So U cross B will give you electric field according to this equation in this direction. So this electric field is trying to push positive charges here, and is trying to push negative charges here, thus creating a voltage difference across this road. And this voltage difference is trying to push a current in this direction. Notice what's happening. This current is trying to create its own flux, and its own flux will be coming out from the page. It's trying to resist the original increase in the flux going through the circuit. And here, as you could see, the flux going through this part is increasing with time because the dimensions of the coil is increasing with time. This is why this current has to be always flowing in this direction. Okay, so solving this problem, we have two ways. Either calculate the flux as a function of time, differentiate it relative to t, put a negative sign, or use this expression and then integrate over this length, this electric field that you calculated, and this will give you the voltage difference across this rod, which is really trying to force the current in the rest of the circuit. Both of them should give you exactly the same answer. Now let's start to see some examples. In the first example, we have a loop, and there are two resistances, 10 ohm and 4 ohm. This loop has a rectangular shape. It has dimensions 0.6 meters by 0.2 meters. There is a flux flowing in the z direction, so this is x, this is y, and z is coming out from the page. It's varying with time. So here the dimensions of the coil does not change with time. The flux going through it is what's time varying. So it is 40 cosine 30 by t minus 3y in the z direction. We assume here that the wires, the rest of the wires, do not have any resistance, and would like to find the current in this loop. This is a very classical application of Faraday's law. We have to calculate the flux going through the loop, and then we differentiate this flux relative to time to get d psi by dt, and then we put it with a negative sign to be equal to the EMF. And once we have the EMF, we can get the current. The current will be equal to the EMF divided by 14, 10 plus 4. And this current, of course, will be in the direction such that it's resisting the change that's happening in the flux. So let's see how we can solve that. So as I said, first let's calculate the flux. The flux is equal to the integral of b dot ds. We are integrating over a rectangular coil from 0 to 0.6, from 0 to 0.2 over y. But the integral over x is not a problem because x is nothing, it is a function of x. So I can simply multiply 40 by 0.6. This will give me 24. I have to integrate this term relative to y. The integral of the cosine will give us sine, and then we have to divide by minus 3 because we're integrating relative to y. This will give us minus 24 over 3 multiplied by the sine. Put the upper limit minus the lower limit. You have this expression here for the flux. So the flux does change as negative sign. The flux does change as a negative sign with time. It's going down with time, and then it starts to go up again. So now we start with, in order to get the EMF, we have to differentiate this expression relative to time, and then put it with a negative sign equal to the EMF induced in the circuit. So when you differentiate this term, the derivative of the sine will give you cosine, and then you multiply by 30 pi. Both terms will give you 30 pi, so I was able to take it out and multiply it by 8. The negative sign will cancel with the negative sign we had earlier. We can now use an identity that cosine u cosine v is equal to minus 2 sine u plus v over 2 sine u minus v over 2. So this is u here and this is v. So when you sum them, divide by 2, you get this term. When you subtract them, divide by 2, you get minus 0.3. Take the minus out, will cancel with the minus 2. Then you end up with this expression here for the EMF. So the 2 here will become a positive as shown here. So this is the VMF. This is the electromotive force. In order to get the current, you divide the electromotive force by the resistance 14, and you see that the current going through has a sign dependence. The current going through has a sign dependence. So does my answer make sense or not? Let's see. When the flux start to increase in the loop, okay, when the starts well, actually, let's assume it starts to decrease first. When the flux going through the loop starts to decrease, then the value, the polarity of the voltage will be plus and minus this way, such that if you close the circuit, there will be a current flowing here that will create also a flux coming out from the page, trying to help it, try to stop that decrease in the flux going through the circuit. So here our answer will be that yes, the electric current created is trying, which has a sine profile. Sine profile means it's increasing with time between these two terminals. So if you close the circuit, there will be a current trying to stop the decrease happening in the flux, because the flux starts as a minus sign, it's decreasing with time. So and you can follow that exactly at every time step. The current will always be such that it's creating a flux that's trying to oppose the change happening in the flux going through the circuit. One other interesting application to Faraday's law is the concept of transformers. Here we have time varying current or voltage applied to this terminal. This results in a time varying current here that results in a flux. This flux will link the other loop, so you get lambda to 1. When this one changes with time, it creates a voltage between these two terminals, and the voltage created is minus the rate of change of the flux, lambda to 1, which is the flux linking the second coil due to the magnetic field of the first coil. And this flux lambda to 1, as we explained earlier, is equal to minus N2, number of turns of the second coil, multiplied by the flux going through the second coil due to the magnetic field of the first coil. And this here is nothing but the integral over the area of the second coil of the first magnetic field. So this is how transformers work. You apply time varying field on one side, you create a time varying flux. This flux links to the other side because it's time varying, it's created its own EMF, and then energy can be transferred to the other side of the transformer. Of course, if there is no time change, then there will be no voltage created between these two terminals. We can take a look at one more example. Here we have a square loop. So there is a square loop here, and it's moving away with a constant velocity u naught from an infinite wire in the z direction. There's a current I flowing in that wire, and it's flowing along z direction. We would like to find the induced EMF. So you can see this current that's flowing here in the circuit. This current, of course, as we have learned earlier, it will create a flux here coming out from the page, and a flux here going into the page. So the flux in this loop is going into the page, okay? And this flux is actually decreasing with time, because as the loop moves away in the y direction, the strength of the field going through this coil is decreasing, because we know that the field of an infinite current, it decreases as 1 over rho. So there will be an EMF created, and so if you create a tiny gap, if you come to this circuit and you create a tiny gap here, a tiny opening here, and you measure some voltage, you'll see there will be some voltage difference measured. And this voltage difference will try to create a current such that it creates a flux helping the decreasing flux going through the circuit. Let's see how this is done. To solve a problem like this, first you get the B resulting from that wire, and then you solve for psi, you calculate psi going through this loop, and because this loop is moving with time, psi will also be a function of time. And then you will differentiate psi relative to t to get the EMF, and this EMF is what, if the circuit of course is closed, is what will create a current. So we start to solve this problem. As we agreed, the magnetic field resulting from the wire will be going into the page at the loop, and the direction going into the page is the minus AX direction. This is why I replaced the A rho by minus AX. And this magnetic field is decaying with rho. The expression for the flux is simply to integrate over the area of the loop of B dot ds. So we integrate over the rho, the variable parameter rho change from rho, certain rho, to rho plus A. Because remember, when you integrate over the coil, this is how your coil looks like. At any time instant, it starts with rho and then it ends with rho plus A. Even though rho is a function of time. Rho is a function of time here. And then the other dimension is not really changing, it's a, you integrate it from 0 up to a. So if we integrate over x, this is x, or whatever they call it here, it's z, actually it should be z. I should be correcting this one, this here should be dz, correct, because you're integrating over z. So you integrate over z from 0 up to a, you integrate over rho from rho up to rho plus a. The integral of z is not a problem because it will give you a. The integral for over rho will give you 1 over rho will give you ln rho, both ln rho plus a, and over of minus ln rho will give you ln rho plus a over rho. And remember that rho has this dependence on time. The rho is equal to rho naught plus u naught t, because this whole loop is moving away from the current. So now we are all set to calculate the EMF. EMF is by definition, according to Faraday's law, is minus d psi by dt. We have here a single loop, so lambda is equal to psi. So we differentiate this term relative to t. The derivative of the ln will be 1 over the number inside multiplied by the derivative of this term relative to t. Remember that rho is equal to rho naught plus u naught t. So its derivative relative to t will give you u naught. And this is why we had this u naught here, and they have this negative sign. You can take rho plus a as a common denominator, and then you subtract them, you get minus a, that will cancel the minus a outside. Then the electromotive force created in this loop, surprisingly, it's always positive. It's always positive. So it is saying, I would show you that now in a second why it's always positive, because it has to continue to create a current in one direction, and this direction must be the direction that will assist the decreasing flux, because the flux going through the loop is decreasing, and the EMF will try to create a current assisting that decreasing flux. So here, because I calculated psi by integrating over this area, the unit normal over this area is actually going into the page. So the direction of dl I should be using for my integration is this direction here. Okay, and you could see, because my answer was positive, this means that this terminal is always positive relative to this one. So if I come now and close the circuit and add a resistor here, then there will be a current flowing in this direction I. It's current flowing here. But what is this current trying to do? This current is trying to create a flux coming out from the page here and going into the page here. It's trying to assist the decreasing flux resulting from that infinite wire. Okay, so this is why you could see here how I selected the direction of ds, how I selected the direction of dl, how I interpreted a positive EMF, and how the current, if you close the circuit, will start to flow. So this current will result in this direction and is trying to assist the decreasing EMF.